Okay, so now we're going to talk about the emax model, which is a simplified model from the sigmoid emax model. The sigmoid emax model had that gamma in here, and here the gamma is always going to be 1. So the gamma disappears as another variable in the emax model. So, but still the effect and concentration are here. So this is our independent variable. So as concentration changes, we see that change in effect. This is our dependent, right? Now, Emax stays the same. This is still our capacity, the maximal effect we can see, and C50 is still our affinity, the concentration where half maximal response is seen. Slope factor we don't have to worry about anymore because slope factor is 1, so it disappears. So it's a little simpler model. So what it's going to look like is this. We have an increase as we increase our concentration, we have a gradual increase in effect. So here, just to practice, what would be the C50 of this model? Well, we go to our 50% effect, although we try to actually be on the line, and then we drop down and see what that concentration will be, which I would say here is 0.1 milligrams per liter. So our C50 is 0.1 milligrams per liter. Our Emax is 100%. This is a percentage. I should say that on there, I'm sorry. So our Emax is 100%. And as we increase our concentration, we will see a gradual increase in effect, and then it will flatten out up here. So what's important about this is that our we don't see this all or none or on off. We only see that with higher gammas. So we don't see that. The response is what we call graded. So it will slowly increase with increasing concentration. Another important factor here is that when the concentration is 0, the effect is 0. There's also a maximal effect beyond which increasing the dose will produce no further effects. So if we go back, we can see as we increase the concentration, as we increase the concentration here, we can see, let me just erase all of this. As we increase the concentration, we can see that there's a minimal increase in effect here. Gotta keep remembering to erase. Wait, I did all that. So there's a maximal effect beyond which increasing the dose will produce no further effects. We get to that flat portion of the curve, and we really don't see much difference. When the high concentration range is reached, as our concentration increases, E does not increase as much. Therefore, the duration of effect will be increased. This is an important point. So the duration of our effect will be increased as we get up into that flat portion of the curve. So if this is our effect and this is our concentration, and it looks something like this, as we get up in this portion of the curve, it's going to take time for our concentration to fall, isn't it? So let's say that this is at a concentration of 10, 5, and then this would be 2.5. Okay, this is not to scale, I guess, but so here, so if we're here, we're going to have 1 half-life and have really no change in the effect, or not much. And then another half-life, we'll start to see the decrease, and then maybe down here 1.25 would be the next half-life, so we'd start to see a real change down here. But you can see if we get way out on this part of the flat part of the curve, then we're going to increase the duration of the effect, because we're going to stay at this high effect even though our concentration is falling, right? So the model really helps us understand duration of effect. It's not going to be a straight half-life situation as far as seeing the effect drop half for every half-life. You might have predicted that before this, but now you know that's not necessarily the case. Now, here's another interesting thing. This is only for the linear. Remember, we're still talking about the emax model, not the sigmoid emax, but the emax model. If we plot effect versus the natural log of concentration, not the concentration, but the natural log of concentration, this is really important. Between 20%, E of 20%, and E of 80%, this is actually a straight line. So we'll see a linear increase in effect as we increase the concentration between these two concentrations. This concentration, a natural log of, what is that, negative 3.75 or something like that, and negative log of close to negative 1, natural log of the, between those two concentrations, we're going to see a linear increase in effect as we increase the concentration. But remember, this is a natural log, so it's not really a linear increase in concentration, but a logarithmic increase. And it's only that natural log, not straight concentration. So here are the learning points here. Okay, between 20 and 80% of maximal response, the relationship between the effect and the natural log concentration is linear. So it's not really linear at all if this natural log concentration is increasing logarithmically. A doubling of the natural log concentration doubles the intensity of the response within this range. So therefore, 80% of E, the concentration at 80% of E is the most efficient dose. What I mean by that is, gotta get ready to erase because I know I didn't erase. If we go to 80% of our effect, remember this is our effect over here. If we go to 80%, this concentration here is our most efficient dose, because as we go up from here, this starts to flatten out, doesn't it? We don't get as much bang for our buck, but this is linear down to here, to 20% of our effect. So this part is linear. This would be considered our most efficient dose. In other words, we're getting the most bang for our buck at that particular concentration. Now, is that always an appropriate concentration? No. So it's limited in its value if you don't know, because maybe there's significant side effects at that concentration. It could be outside the therapeutic range. Okay. That's it for our emax model. Next, we're going to talk about our linear model.